let's start the discussion of numerical methods. This is basically a root finding methods. So in numerical methods, you can find a root uh, that is a function that is exceeding fourth degree. So it is recommended that you have to use numerical methods for a degree in a function which is degree greater than 3, which is, for example, x4, like that one. So let's start with bisection method. So bisection method is particularly a part in bracketing method, which is a meticulous method in the numerical methods solution. So basically, this is the definition of bisection method. It is a bracketing method of finding the root between 2 points. Since the root is bracketed between 2 points, let us say x1 is the lower limit of value of x, and x2 is the upper limit of value of x. So one can find midpoint x mid between x1 and x2, which gives the new interval x1 x mid or x mid and x2. So it is also used to determine the roots of an equation by repeatedly bisecting an interval and then selecting a subinterval in which the root lies. So for example, this figure, this is the graph of a function sine x. So as you can observe, the graph of function sine x is a sinusoidal wave motion. Okay, so meaning the root of this function is always lies on the x-axis. So for example, this is now the root as, uh, as we can determine in graphical approach. Now in the bisection method, you are guessing. For example, this is point x1. Say this is now the root that, for example, this will be my root, so x1. So this is a guess. And then particularly x2, this is also a guess. This is another guess of a root. So particularly in the say x mid, that is x1 plus x2 over 2. So that is considering a to be closest to the root of this function. So if f of x1 and f of x mid have opposite signs, so a root lies in x1 and x mid. So meaning the root lies here in x1 and x mid. If they have opposite signs when you are evaluating the function. So given two values of x1 and x2 in which x1 is less than x2, and if you multiply the results of f of x1 and f of x2 less than 0, so the function of f of x must be continuous in this range of values and is positive at one and negative at the other. Similarly, x1 and x2 must be of opposite sign interval. Additionally, if we divide the opposite sign interval in half, one or the other half must end up being another opposite sign interval. So we keep repeating this procedure until the opposite sign interval is so small that any point in it is within the specified tolerance. So to be more accurate, consider the point x mid equal to x1 plus x2 over 2. So look at it over in figure 2. So this is a graph for illustrating bisection method. For example, this is now the graph of the function. So the root is particularly here. Okay. So we have initial guess here at x1 and also here x2. So if we have if f of x mid is 0, then automatically we get the root. Otherwise, depending on the sign of f of x mid, the root lies in either x1 x mid or here x mid x2. So in any case, the opposite sign is now half as large as before by repeating this process with a new interval. It will sufficiently become small. So to showcase this, to shortcut this, how to solve using bisection method, I have shown here steps. So particularly, this is now the steps to find a root of a function rather using bisection method. So number one, you have to choose x1 and x2 as initial guesses such that f of x1 multiplied by f of x2 is always less than 0. And number two is you have xm, so meaning I put subscript here xm, so that means x mid equal to x1 plus x2 over 2. And then step 3 is find the product of f of x1 multiplied by f of xm, and then we have three output values that we have to get. So it is less than 0, greater than 0, or equal to 0. So this is now uh, particularly the case of evaluating the f of x1 and f of xm. So if f of x1 multiplied by f of xm less than 0, then x1 equal to x1 and x2 is equal to xm. So this is our new roots based from the initial guesses of x1 and x2. Now, in the second is f of x1 multiplied by f of xm greater than 0, then x1 is equal to xm, x2 is equal to x2. Then, lastly, if f of x1 multiplied by f of xm 0, then root is equal to xm. So we should stop because we already find the root. So step 4 is find xm, x1 plus x2. Here is the absolute error. So we have here, I have absolute value of xm new minus xm all because our midpoint will be changed, particularly by setting different x1 and x2. Multiply by 100. So check if the error is less than or equal to the specified or free specified tolerance. And then number 5 is go back to step 3. So actually it will play around here in step 3 method. So example, I have here a find a root of equation f of x is equal to x squared plus 3x minus 4 using bisection method. Correct to 3 decimal places. And then I have set here the initial guesses x1 equal to 0 and x2 equal to 1. So, but before that, I have to show the solution, how to solve particularly the roots of an equation, because we can directly solve its roots using any method that we have learned. Example, completing the square, you can say quadratic equation, and also factoring. Okay, so I will use Jamboard app of Google here. So I will write the function of x equal to x squared plus 3x minus 4. That is the example that we have presented in the 4 bisection method. So let's go directly to find the roots of this function. We can use completing the square, factoring, and also quadratic equation. basically this function is a degree of 2. So we can say we can factor directly this by uh, say so x minus 1 and then also multiply by x plus 4. Okay. Okay. So if we have to check this is negative x and this also this one, this is 4x. Particularly if we add this one, this will result to 3x. So this is correct. So we have to evaluate this equate to 0. So x minus 1 equal to 0. So this is now our root 1. X1 equal to 1. Okay. And then also we have x plus 4 equal to 0. So again, we have x2 is equal to negative 4. Okay. So particularly, this is now the roots of the function of x equal to x squared plus 3x minus 4. Okay. So if we can say that this is now the root of the function, say, okay, so we have to substitute here. For example, f of x1. So f of x1. So that is equal to f of 1. Okay, so that is equal to 1 squared plus 3 times 1, 3 times 1 minus 4, so that eventually that is equal to 0. So meaning this root is a root of this function because the function of x is equal to 0. That is our ultimate solution in finding the roots. F of x should be equal to 0. Okay. Next would be f of x2, which is negative 4. Now, if you substitute this value, x2, say negative 4, f of minus 4. So eventually that is equal to 0 already. Because negative 4 squared, that is 16. 16 plus 3 minus 4, that is 16. Minus 12, that is 4 minus 4. So eventually this is a 0. Okay. Okay, now, so we have already known how to solve the function or finding the root of the function using directly the solution, that is, for example, factoring, so we can find the roots of a function. However, in numerical methods, we have to deal with a numerical solution, which is a very iterative process or a very meticulous process in finding the roots. So that is designed for a greater degree of function, as I said earlier. So for example, if this is x4, this is a very already difficult or complex process. Okay, now So, okay, okay. So for example, let me back here in my presentation in PowerPoint. Okay. So example, find a root of equation f of x equal to x squared plus 3x minus 4 using a bisection method. Correct to three-decimal places. So the initial guesses is x1 equal to 0 and x2 equal to 1. So that is merely on the first step, we have to choose x1 and x2 as initial guesses, such that f of x1 and f of x2 is less than 0. So let us check this first procedure. So solution. So f of x1, so meaning I will evaluate this given x1 0. So f of 0, so meaning I will be back here in the given function. So 0 squared plus 3 times 0 minus 4, that is minus 4. So f of x2, so f of x2 is 1. So f of 1, so meaning that is 1 squared plus 3 minus 4, 0. So meaning I have here 0. So if I will evaluate this f of x1, f of x2, so that is um, negative 4 times 0, that is 0. So it falls here that if f of x1 in this statement, if 0, then we have already find the root, which is the root is negative 4. Okay, so we continue in the next step of this procedure. So it's xm, x1 plus x2 over 2. So meaning x1 is 0 plus 1 over 2, that is 1 over 2.5. So, for example, f of xm, we have to evaluate this using this. So I will show the solution in the app. So for example, we have f of x equal to x squared plus 3x minus 4. Okay, so we have to evaluate this f of 1 half, or that is 0.5. So 0.5. Okay, so this is 0.5 squared okay plus 3 times 0.5. So I'm sorry for using mouse and I'm new to this. 3 times zero point 0.5. 0.5 minus 4. Okay. If we have to evaluate this one, f of 0.5, so you check in your calculator later, or if you have a calculator there, you can also recheck. So we have 2.25. So this is 2.25. Okay. So we will back here. So we have rather negative 2.25. Okay. Now, so in the next step 3, we have to evaluate. Say f of x1. We have f of x1 is negative 4. Okay, multiply by f of xm, that is negative 2.25. So this is equal to 9 because negative 4 is f of x1 multiplied by f of xm, that is negative 2.25 multiplied by negative 4, that is 9. So meaning basically this is greater than 0. So if greater than 0, this is now the new bracket of root. So meaning our x1 will be equal to xm. So our xm is 0.5. So we have here. And then our x2 will be remaining 1. So the new bracket of the root lies between zero point 0.5 and 1. So we have to get the new midpoint, which is I have subscript here xm1. So for example, x1 plus x2 over 2. So meaning our new x1 is 0.5 and then x2 is constant 1. So 0.5 plus 1 over 2, that is 0.75. 1.5 over 2, 0.72. Now, again, we have to evaluate this one. So f of xm1. So again, we have to substitute this 0.75 to this. Okay, gets? So that is f of xm1 negative negative 1.1875 rather. So f of zero point 0.5, which is the f of zero point 0.5 is now the f of x1. Okay, multiply this by f of xm1, that is negative 2.25 times negative 1.8 1.1875. So this is the result. So meaning 2.671875 is greater than 0. So meaning if greater than 0 again, this is now uh, the new bracket of the root lies between 0.75 1. So meaning, as you can see, that the numerical solution is converging to 1. Okay, so step 4 could be also using the specified tolerance, but in this example I have not given the specified tolerance, so it's better to have this in the looping of problem here. Step 3, we have to focus here in step 3. So meaning the new bracket of the root lies between 0.75 and 1. So the new xm2, or the new midpoint, will be x1. So our x1 will be now equal to xm. Okay, which is 0.75. So 0.75 again, and x2 is remaining constant, which is 1. So 0.875. Again, you have to evaluate and substitute this 0.875 here. We have to get here. You can get here. You can get this. Okay, now multiply again by using this one. So f of point, because this is point, this is f of x1, xm2, so meaning this is 1 here. So if I have to evaluate this one, so 0.723, the result of multiply of this 0.75 again, f of 0.75 is negative here, negative 1.1875. Multiply by f of mx2, which is kani, which is this. By using this is, we have get this value greater than 0. So if greater than 0, then again, x1 is equal to xm. So meaning, our x1 is equal to this xm, 0.875. x2 will remain 1. Again, we have to follow again the step 2, which is xm3. This is now x1 plus x2 over 2. So 1 half x1 is 0.875 plus 1. So we have this 0.9375. So evaluating this value using this value, we have get this value. Again, this is f of x1 here, which is 0.875, and then f of 0.875 we have here. We have get this value. Okay. So negative 39 over 64. Okay, multiply by this value we have get from the midpoint resulting to this value. Again, greater than 0. So the new bracket of the root lies between this particularly value. Particularly this value is 0.9375, which is our new x1, and then x1, x2 rather. Okay, so our xm4 will be x1 plus x2 over 2. Again, we have this value. So as you can see, this is a repeated process. As I can see here, this is a repeated iterative process. But however, this is a brute force solution in finding the roots of the function. However, we have to learn this one because, as I said earlier, if the equation is greater than 2, let's say x5 plus or x6, x10, we have to use numerical methods. Okay, let's continue. So if we have to evaluate f x m4, we have this, and then multiply. Okay, so as you can see, the new bracket root lies between these. Okay, now you have to go to this process by solving it, and then so repeating the process of iteration, it converges to the root of the function. So the table below represents the xm of continuous iterations. So I put this in table. I use MATLAB in getting the iterations of these values. So for you as a student, you can you can store functions like this in your calculator, and you can um, repeatedly solve using the bisection method or the iteration process. So here I stop here because it converges already to the root 1.0. So I have made a conclusion here. The function f of x is equal to x squared plus 6 minus 4 has two roots, which is x1 equal to -4 and x2 equal to 1. So for the root x1 equal to -4, let's consider the initial guess of the root between -5 and -3. So if you have, say, example, x1 plus x2 over 2. So -5 minus 3, that's -4. So if I have to evaluate f of the x1, which is f of -5, so -5 squared plus 3 minus 5 minus 4, that is 6. So again, for f of x2, this is f of -3. So -3 squared plus 3 minus 3 minus 4, that is -4. So our xm is -4. So f of -4 squared plus 3 minus 4 minus 4 is 0. So since f of x1 is 6 multiplied by the f of xm0, then the root is equal to xm, is -4. So the function f of x, x squared plus 3 can be graphed using MATLAB, and the roots of this function can be determined using graphical approach for finding a root using the graphical approach. So it must be kept in mind that the root always lies on the x-axis, and we should always consider function of x equal to 0. So this is now the graph of the function. Particularly, this is a parabola that is opens upward. So as you can see, if you bisect, this is now the x-axis. So that is the root lies between, also meaning the crossing of the function x squared plus 3x minus 4. This is and -4. This is the graph of this function is -4, 0, and then this is 1, 0. So thank you. That is the end of the bisection method, and we'll continue on the next bracketing methods in the next video. Thank you.